lecture. So this week, this is a special week. This is something how we discuss about this modern view of physics. So maybe last 2 months, yeah, over 2 months. Over the last 2 months, I think we have discussed about classical physics. Yeah. So classical physics usually, the birth of the classical physics usually before 20th centuries, okay, before 1900, the year. So after 1900, we call it the modern physics. Why? Because after that time, we introduce some new, completely new of the ideas about physics, because somehow we need this idea to explain how microscopic world works. Okay, so that's why we call it this modern physics. But this is in Indonesian, in bahasa, but I will speak in English. We will summary, maybe I will summary in bahasa at the end. So in your SAP, the modern physics, we only discuss for dualism property. Okay, but if we talk about modern physics, it is not complete, yeah. If we do not discuss about relativity. Okay, let us start. Okay, this is the global picture of modern physics. It's a joke. So this is what is overview of our lecture today. So basically, we will discuss shortly about special theory of relativity, because this is also one of the most important theory in modern science and in modern physics. And then we talk about dualism property of wave particle, and also about atomic model, Rutherford and Bohr, and quantum mechanics. So on Friday, I think I will continue the lecture for the first 1 hour, and then the second hour, I will continue with the tutorial session to discuss about, because it's quite a lot about this modern physics, because I think last year or last 2 years, I taught also modern physics. Yeah. But this semester, I'm teaching special theory of relativity. It's an elected course for theoretical physics. So the development of physics until 19th centuries, we have Newton mechanics and Maxwell theory of electromagnetic, and also some development of physics at the end of 19th centuries. Okay, we have Newton mechanics. So basically, Newton mechanics formulated by Isaac Newton, and he wrote a book about Principia, we call it. This is written by Isaac Newton in around 1686. Yeah. This one is quite old book about classical mechanics, we call it. Okay. So the Newton's law also written by Newton in this book, and also some theory of Newton about light, for example, and everything. If you have a chance, any of you have visited Cambridge? Any of you? Hello? Any of you have visited Cambridge? No, no one. Okay. So if you have a chance visit University of Cambridge, there is the University of Cambridge divided by several colleges, and the best one, I think the best one is Trinity College. So Trinity College is also Newton was studied there in Trinity College. There is also a museum in Trinity College, and they have also a museum, a science museum, and also they have this book. Yeah, it's not for borrowed, but it's a collection, museum collection. This Principia, it's old book. Okay, the Newton's law, we know about these laws of motion, Newton's law of motion. We have 3 laws of motion, and also optics, the theory of Newton about the light, and also he formulated a calculus. You also studied, you're studying calculus this year, this last semester also, this semester about differential and integral. And he formulated independently from this like this. So, well, there is a versus here, a clash between Newton and Leibniz, Gottfried Leibniz. Gottfried Leibniz is a mathematician, a German mathematician. So somehow they clash about who is the who formulated the calculus, who did formulate calculus. It's an old joke story, a funny story, I think, between them. And also Newton's formulate the theory of gravity, as we know. Okay, so gravity it's different, this is law of motion, and this is theory of gravity. So gravity is the example of interaction caused by mass. So the mass here is the gravitational mass. In Newton's law of motion, he also introduced the mass, okay, a mass, but this is inertial mass, okay. So this inertial mass is different from gravitational mass, okay. But there is a principle, we call it the equivalence principle, that states that this inertial mass is coincide with gravitational mass. Okay, this is experimental by at first, using Cavendish equilibrium stuff, something like that. So this is what we know about Newton's law of motion. Okay, the first law is about equilibrium. Okay, and the second one is about the external perturbation. The external perturbation is it's about why, for example, a particle or a body, they can change the state, because the external we call it perturbation. Just a moment. Okay, so the third law is about action and reaction. Okay, but the third law, at least we have two bodies. Okay, for action and reaction, and also the Newton's law of motion. There is also we call it Galilean transformation. So Galilean transformation, it's a transformation between two inertial laws. Okay, so inertial laws means that a body who is in equilibrium. So it means it at rest or move under a constant velocity. Okay, so there is no force acting on them, acting on it. So before 1900, this Newton mechanics is really successful, yeah, explaining the dynamics of particle or body at that time. Okay, in Newton mechanics, we have a special reference. We call it inertial reference. Okay, so where the inertial reference is the reference to satisfy the Newton's first Newton's law of motion. Okay, so this is the inertial frame or inertial reference. Okay, so the relation between inertial frame or reference is by using this so-called Galilean transformation. So basically, this is the Galilean transformation. For example, if you have a reference O and O prime, O is moving toward along this x-axis of O, okay, with the velocity v, something like that. So this is the Galilean transformation. Okay. On the other hand, we also have Maxwell theory of electromagnetic. Okay, but this is Maxwell theory of electromagnetic based on 4 equations coming from who's derived from Friedrich Gauss, Michael Faraday, and Ampere. I don't know Ampere, Andre Ampere. I forgot the name, the formula. And also Lenz, something like that. But we could simplify to statement that so the electric field can be produced by the change of magnetic field, and also the other way around. The magnetic field can be produced by electric current or the change of electric field. Okay. So the implication of Maxwell equation, we have electromagnetic wave, how we have discussed maybe last 2 weeks or 3 weeks. Okay, so this is basically new. Why? Because this electromagnetic field can propagate through vacuum without medium. Okay, so somehow it's opposite with the mechanical waves. Okay, mechanical waves or something like that. So also this Maxwell theory of electromagnetic gives an idea about unification. So the electrical phenomenon and the magnetic phenomenon is somehow equal on the same footing. We call it in English. Okay, they basically equivalent. Okay, and also from this electromagnetic wave, yeah, we have produced also this C here, which is the velocity or the speed of light in the vacuum. It's around this one. So at the first time, this Maxwell equation, this Maxwell idea about electromagnetic field can be applied to explain the phenomenon of interference of the light, yeah. But it is not really successful until Frank Hertz generate this electromagnetic field, yeah, using an oscillation like antenna-like generator, something like that. So at the end of 19th century, somehow we think that the physics is already complete. We have optical theory, kinetic theory of gas, electricity, magnetism, and so on, everything. Yeah. The last invention or discovery about X-ray by Ronson, and also electron by Thomson, and radioactivity by Becquerel, and also the Curie, this polonium. And this guy also become Nobel laureate, yeah? Ronson, Thomson, Becquerel, and the Curies. So there is also, we call it black body radiation. So basically, a black body radiation is, for example, is very ideal body who absorb completely the light. Okay, it cannot emit anything except absorbing the light. Okay. But the other way around, we also call black body if a body is a perfect light source, like the sun. Okay, the sun, we call it black body, because the sun always emits the radiation, emits the light, okay, the light radiation, yeah, electromagnetic radiation, okay. So the sun, in fact, is not absorbing any light, okay. It differs from black hole. For example, black hole always absorbing the light, classically. That's why we call it black body. So black body means that the perfect body, a body which perfectly absorbs the electromagnetic radiation, or it is a source, an ideal source of electromagnetic radiation, like the sun. Okay. So basically, there is an experiment at that time by Wien, who study about the radiation, electromagnetic radiation from the sun. Somehow they have particular distribution, which is the classical theory cannot explain why this is so. Also, Albert Einstein in 1905, he published 5 papers in Annalen Physics. Okay, this is already quite famous journal at that time, and there is also still exists this Annalen Physics. It's German scientific journal about physics. So he published about the theory of photoelectric effect. Okay, and so he became Nobel laureate in 1921 because his theory about photoelectric effect. Okay. And also he published about Brownian motion. This is the proof the existence of atom at later time. And then he also published about relativity. Yeah. If you read the paper, Einstein didn't say about this one. Okay. But this is the implication of this paper, okay, by him. And also, he also published also the second paper about relativity. Okay, so the first time is about the foundation of relativity, and this is the implication of the relativity. And also, the first one, the last one, is about the dimension, molecular dimension, and this is his PhD dissertation. So only three of them, photoelectric effect, special theory of relativity, becomes the cornerstone in physics history. So we came to special theory of relativity. So this is the background. Why we need this special theory of relativity? So at that time, around 1900, it's around 1900. It means before, maybe 10 years before, and 5 years after 1900. So at that time, we have two established theories, that is Newton mechanics and Maxwell theory of electromagnetic. Okay, but somehow these two theories are not compatible into each other. Okay, it means that compatible. It means that the Maxwell equation is not invariant, we call it, and under Galilean transformation. So the implication is that this electromagnetic theory, it depends on the motion of an observer. It depends on the observer motion. This is not good, okay? So somehow this electromagnetic theory should be equivalent, whether the observer is at rest or the observer moves, okay? And also, there is also a problem that the speed of light is not a constant also, and it depends on the observer motion. And then we have also a problem because at that time we only knew about the mechanical waves, which can propagate only through mediums. Okay, but this is the concept of electromagnetic field that can propagate without a medium is very strange at the time. So for solving this problem, somehow the physicists at that time propose a medium, we call it ether. Okay? This ether, okay, it's not related to this in chemistry, this ether class of what we call it. Just now etherless, itu beda, it's different. This is, we call it, this ether is a medium for propagating the electromagnetic wave. In this case, is the light. So, and also these Michelson-Morley experiments, okay, they get this value, okay. It means that because it's very small here, but somehow we can say that the speed of light in the vacuum is somehow, well, we can talk it as a constant, okay, a constant, universe constant. Well, it's a belief, okay, it's a belief. So somehow this fact somehow is different from this assumption. Okay, to solve this problem, okay, somehow Einstein formulated the postulate of special relativity. So these two famous postulates, it means that this, we call it the principle of relativity, which state that the law of physics have the same form in any inertial frame. Okay, so you see that this statement is very simple. Okay, but the difference between this statement about inertial frame fundamentally, basically, it's different from the Newton. Okay, so the definition of inertial frame in this case is the same as Newton did. Okay, the definition in Newton mechanics, this inertial frame, between the frame is at rest or the frame that moves at constant velocity, with constant velocity. That's the same definition. But the formulation in this case is different, okay? The Newton mechanics is formulated in three-dimensional space. Okay, three-dimensional space. So our universe is three-dimensional space, okay? With time is only a parameter, not the coordinate. Okay. Einstein formulated the theory of relativity using the space-time. It means that the time is no longer only a parameter, but it is the behavior of the times is similar to the space. Okay, similar. It means that we have the difference properties. There is a difference properties of time, that time is different from the space, from the spatial component. Maybe we call it space. Okay, so somehow this principle of relativity in this case is formulated by Einstein in 4 dimensions. Okay, that's the difference. And then the second postulate is the speed of light in the vacuum does not depend on the motion, the observer motion. Okay, so somehow the speed of light in the vacuum is constant. You can say that. Okay, is there any question until this section? Any question? Any question? Hello, hello. Any question? No question. Okay, no question. Okay. So about okay, I can skip this one. You can read in the book, yeah. Okay, about this relativity. So basically, we have this formula. Okay. So somehow the time in this case is relative. Okay. So this is, for example, for time is at rest, and this is in the moves. Okay. Or we could also, this is at rest, and this is delta t, we call it the proper time. This delta t, and this is not the proper time. U is the velocity of a frame. So we also have a line contraction. I will give you only the formula. We call it Lorentz contraction. Lorentz line contraction. Okay, like this one. Okay. So in relativity, we replace the Galilean transformation by the Lorentz transformation. Okay, this basic Lorentz transformation is the transformation in the space-time. It's no longer in space, okay? It's in space-time. So in space-time, we have this Lorentz transformation. So this inertial frame or reference in this case is related by this transformation in the space-time. Okay. So some points should be focused on that in the special relativity we do not introduce force concept like in the Newton. Somehow the force in this case is quite different. Okay. So formally, the specialty of relativity is formulated in the space-time. This we call it this Minkowskian geometry. So this Minkowskian geometry is a space-time geometry. It's a flat, yeah, and the coordinate is like this: x, y, z, t. Okay. So well, it's very. This Hermann Minkowski, who formulated this Minkowskian geometry, is a teacher, Einstein teacher in the class. Yeah. Somehow this Hermann Minkowski have a funny relationship with his student Albert Einstein. So he called Einstein is a lazy dog. Yeah. I don't know. Maybe this is in his view. Okay. So in this case, for example, we have also the energy and the mass. Okay. So in relativity, in special relativity, we introduce M0. M0 is a body mass at rest. Okay. And then we have also introduced the total energy of a particle or body. Okay, this is equal to M0 C squared over square root 1 over V squared over C squared. And the kinetic energy is the difference between total energy and the rest energy. Okay, so this is the rest energy. If we call it V equal to 0, then the kinetic energy vanishes, but E is not vanishes. So this is, we call it this rest energy. Okay, so this means in this case we have this equivalence between the mass and the energy. Okay. Usually this formula mostly used in microscopic, subatomic physics or particle physics to explain the bending energy, for example. And then we also have the relativistic momentum like this, okay? And then, okay, using this one and this one, the total energy, we could get this formula, okay? Somehow the total energy is related to the momentum. Okay. So this is the total energy for massive particle. For massless particle, massless means we have the zero mass rest mass, the zero rest mass. Okay. So we get this formulation. Okay. So the massless particle, the energy only depends on its momentum. And it moves with the velocity, the speed c. Okay. Is there any question? Any question? No question. Okay. Let us continue. Because the relativity, the special theory of relativity, is formulated in the Minkowskian dimension in space-time, okay, we can divide the geometry by 3 regions, okay. The green one, we call it time-like region, okay. This is the region where the particle that moves less than the speed of light. This C here, the green one, okay. So basically, the particle who lives in this green one, okay, they have rest mass, yeah, and it means that they are massive, okay. And the speed of these particles are less than the speed of the light in the vacuum, okay. And the region in the green one here, okay, we call it time-like, and it's also satisfy the causality condition. Somehow we have this causality condition, yeah, because we can distinguish between the past here and the future. Okay, we can distinguish, and this is for the present here. Okay, so we live as a massive particle. The human live in this green. Okay, because we experience causality. Okay, causality means we have just a moment. In English, it's about causality. It's about we have first cause, and then the implication of the sebab akibat, ya, in Indonesia. I don't know what is in English. Yeah. It's about causality, cause, yeah, and the effect, the after cause. Okay, sebab and akibat. Jadi somehow sebab mendahului akibat in this case. We have cause first and then the implication of the effect. And then we have this light cone here, the white one. Okay, this light cone. Yeah, we have this is the present and this is the future and this is the past. In this case, the light also experiences the causality, but it could also experience non-causal. Yeah? It means that because somehow the future cone and the past cone somehow is connected by this one point. So somehow the light can experience non-causal. Okay. And then blue one here is, we call it the space-like region. Okay, this is hyperboloid. This is hyperboloid. The green one is hyperboloid. The blue one is also hyperboloid. Yeah, also hyperboloid. Okay, but this is non-causal. Yeah? So this is non-physical. This blue one here. So this blue one here is the space in which a particle whose the speed is greater than the speed of light in the vacuum. So somehow this is non-physical. So this is the explanation. Oh, okay. This is for special relativity. Is there any question? Any question? Reno, nggak bisa ya. Sultan.
Ya, Pak.
Ada pertanyaan nggak? Any
Masih
question?
kebauan, Pak.
Kalau tidak ada, nanti di akhir kuliah saya akan tanya, kasih kuis. Oke, tidak ada pertanyaan. Oke, good. Berarti sekarang saya bisa lanjutkan lagi. Oke, can we see slideshow full screen? Halo?
Bisa, Pak.
Yes, Pak.
Okay, this is full screen or not?
Yes, Pak.
Okay. Okay, so this is in SAP about wave-particle dualism or particle-wave dualism. Okay. So this is the overview of our lecture today. It's about a particle property of the wave and this wave property of a particle. And also this uncertainty principle of Heisenberg. So this is the overview about particle properties of the waves. Okay, we start by the Planck theory of black body radiation, effect, the photoelectric effect, Compton effect, and dualism properties of light. So this is the picture. Yeah, this curve here is produced by the experiment by Wien. Yeah? Wien. Okay, this Wien. Okay, so this is the Rayleigh-Jeans law. So basically, Rayleigh and Jeans wants to develop theory that could explain this phenomenon, but the formulation, the theory somehow meets this ultraviolet catastrophe as the theory, as the wavelength becomes shorter. Okay. So basically, this coming from, so Maxwell is a physicist who also formulate this kinetic theory of gas. Okay, we call it Maxwell-Boltzmann function. Yeah? It's related to the probability function of a particle in the gas. Okay, the distribution is like this, Maxwell-Boltzmann distribution function. Okay, so somehow this is the number of molecules and this is the speed. Okay, so we have that, for example, if the molecules, the speed of the molecule is greater, the probability becomes less, becomes smaller. Okay, but somehow they have an optimal. The speed, which is the number of the molecules, is the most one. Okay, the most. This is the maximum. The number of the particle is maximum. So this is at rest. Okay, the at rest, the probability is also smaller. Yeah, it's the same thing. The same thing. And also we have Ludwig Boltzmann. Yeah. This is also the father of statistical mechanics. Okay, he introduced the concept of entropy. So entropy somehow is proportional to the log of W. Okay, this K here is a constant. This is the log. This W is related to the distribution of particle. Okay. So somehow, if the system become chaotic, for example, then the change of this entropy become positive. Okay. So the process becomes irreversible. Irreversible means that we cannot backward in time, in the sense like that. So we cannot somehow, if for example we have the process from 1 and 2, at the end we have 2, okay, we cannot somehow reverse it to process 1, to reverse back, okay, to reverse back the process from 2 to 1. So somehow this is, we call it. So this distribution, this W here, is depend on the number of particle. Okay, so if the number of the particle increase, so W also increase. Then the change of S, okay, the change of this entropy also become positive. And then the system become more chaotic. Okay, just for example, you see that this is, for example, in geography about population. Okay, so for example, in the city, in which the population, for example, only 60,000 city. Usually in Europe, the city with this 60,000 population, we call it big city. Okay, so this, for example, this city with 60,000 population, if we compare, for example, with Bandung, Bandung is around 2 million population. Okay, but in this case, in our level in Indonesia, Bandung is a small city with 2 million population. Okay, but in German, for example, 60,000 population is become a city, a big city in German. Okay, that's the minimum. Okay, so it means that in Bandung we have more. The change of the population, the change of the entropy in Bandung is more positive compared, for example, the city in a German for 60,000 population. Okay, so because this delta S, we call it the change of the entropy, is positive, it means that more chaotic is the system. So for example, we have more problem. In Bandung, we have, I think 5 years ago, or 6 years ago, maybe, I forgot. It's quite long. So Bandung city becomes chaotic in handling the garbage. Have you ever heard, if you are coming from Bandung originally, you have heard about this garbage problem. Okay, so it means that more population, we have more problem. Okay, for example, how to manage the garbage. This is also this certain management. Okay, how to manage the garbage. Okay, and also about garbage and also about sanitation. We have a problem also about sanitation. And then can you mention about the problem in population? Jobs, for example. Jobs in Bandung compared in Jakarta, it's very limited in Bandung. I don't know if in this case we have online jobs, yeah, maybe online job if you include the jobs that is online, yeah. But compared to Jakarta, the jobs in Bandung is very limited. Yeah, that's also the problem. Anything you can mention about the problem in population? Garbage, what else? Poverty, sanitation, yeah, poverty, jobs, and everything. So it means that if the speed of the population positive, it means that every year the number of population increases, so we have this positive entropy. And the system become more chaotic. So it means that we have more problem. How to manage things. Okay, that's the idea of entropy. Is there any question? Any question? Any question? No. Okay. Continue. So this is the intensity of the radiation that emitted by the black body, the black body radiation. The intensity is proportional to T or to 4. Okay, this E sigma A T. Okay, E sigma is, we call it this Stefan constant. A is the area of the black body, this black body. The T is the temperature of the black body. E is a constant, is related to the property of the black body. E equal 1 means that the black body is an ideal. Okay, an ideal means that it's complete. It's ideal for the source of the light. Okay, the source of the light, or it is completely absorbing the light. Okay, that's E equal 1. For E equal less than 1 but greater than 0 is physical black body. So we see that, for example, for normal temperature, we have low intensity, but the effect is very small. Okay, you see from this one. Okay, the bright one here, the temperature in this bright one is hotter, is greater or hotter than this one. Okay, so somehow if we heat, for example, a metal or a thing, a glass or something like that, they will something like becomes bright. So it means that this thing here is also emitting the electromagnetic radiation. Okay? So this emitting electromagnetic radiation indicates the temperature. Okay? If this becomes brighter, then the temperature increasing. Okay. If, for example, this becomes red, then the temperature becomes decreasing. So if it becomes white, okay. So this glass here, this thing here, becomes hotter. Okay. So this is the black body radiation, something like that. So this is the intensity and this is the frequency. Okay. This blue line here is the black body radiation at this 3000 Kelvin. Okay, this yellow one here is 5000 Kelvin, and the red curve here is 6000 Kelvin. Okay, if you see that from these three curves. Okay, this maximum somehow shifting, yeah? Shifting to the right. Okay, so this shifting, it means that the frequency becomes greater. Okay, so somehow the frequency increasing. Okay, as the temperature increase. So somehow we call it this Wien's law of shifting. Yeah? So they satisfy this maximum, this peak of the curve, this lambda p, it's mean peak here, the maximum, times t, yeah, t is the temperature, is a constant here, like this. So, for example, we could estimate approximately the temperature of the sun surface, yeah, using visible light. So the sun surface, using this wind law, okay, we could estimate that the sun's temperature at the surface, the sun surface temperature is around 6000 Kelvin. Okay? So this is the advantage, how we know about the surface temperature of the sun. So 6000 Kelvin, we cannot use hydrargyrum. This hydrargyrum, I mean, I think there is no fluid or things can be reach this temperature. Okay, 6000 Kelvin. It's very big. Okay, so using wind shifting law, we could estimate the sun's temperature, yeah? The surface sun's temperature, 6000 Kelvin. It's quite big. So this is basically it's the picture, yeah, wavelength versus 1/T. It's linear. So this curve, yeah, is produced by wind using via experiment. Two physicists, British physicists, James Jeans and John Stuart Lord Rayleigh, attempt to formulate, to explain this data, okay, Wind's empirical data. But their theories failed as lambda becomes shorter. Okay, this is, we call it this ultraviolet catastrophe. Okay, this one. But somehow we have to modify the theory. Okay, so Planck successfully formulate the theory. This is, we call the Planetary of black body. Okay, so basically he assumed that the energy of black body radiation, so coming from the oscillator. Okay, so this oscillator, the energy is proportional to the frequency. Okay? Just omit this one. Okay, just this one. So classically, the energy oscillator, as you have studied, proportional to what? Bagas, Irfan Nuriski. In classical physics, the energy of oscillator is proportional to to what? Oscillator. For example, a harmonic oscillator. Hello, Bagas.
It's proportional to
Riandito, wait.
Yes.
Yeah, in classical physics, the oscillator, the energy of oscillator is proportional to hello.
The current, the
Senin.
Yes, Pak.
Yeah. What is your answer?
The energy, right? The energy is proportional to what?
Yes.
Is that the question?
In classical physics. We have discussed, I think, about oscillator harmonic oscillator. So the energy of harmonic oscillator is proportional to tick to tick, dot dot dot. Nicholas Arianda.
Yes, sir.
Yeah. What is your answer?
Is it angular frequency?
Sorry? Hello, your answer? Sorry, can you?
In classical physics, sir?
Yeah, in classical physics. In West theory, for example.
Is it amplitude?
Yeah, amplitude squared.
Oh, okay.
Okay, good. Is there any? Okay, so in classical physics, the energy of an oscillator is proportional to square amplitude and angular frequency squared, okay, omega. But Planck proposed that the energy oscillator, in this case, is only proportional to frequency. Yeah, so proportional to frequency, it means that this we have an n here, a constant, an integer, and h is a constant. Okay, so basically this formulation is the Planck guess. Okay, he guessed that this the energy oscillator should satisfy this one. Why he guessed like this? Because they have to satisfy this one to get this one, okay? And this one, the picture is like this, okay? This is the Planck laws, okay? This is the empirical laws, Wind's empirical laws, and this is the Planck laws of black body radiation. So somehow, by guessing this energy, this Max Planck could obtain this result. This very nice result. Okay. So what basically Planck introduced later time, we call it quanta. Quanta means a package, an energy package. So this energy package is proportional to its frequency. Okay. So somehow this oscillator is related to atomic oscillator. Okay. Because at that time, atomic oscillator it's an abstract concept. Yeah. An abstract concept because at that time we do not know about the atomic structure. Okay. But somehow this proves that this energy of electromagnetic radiation is quantized. Terkuantisasi means quantized. Okay, let us continue with photoelectric effect. So photoelectric effect means that if the lights incident coming to falls to the metal, okay, and the metal somehow will ejected the electrons, the outer electrons of the shell, okay? And then it is detected by electric current. It is detected as an electric current. So basically, photoelectric effect discovered by from Hertz around 1887, and then characterized by the Lenard. So basically, the light falls into the surface of the metal, and then these electrons become excited. Yeah, somehow the electron become excited and then release, release from the atom. So this is basically the photoelectric equipment. Okay, we have this vacuum tube. Okay, we have the source of the light. We have this metal. Okay, this is a detector. Sorry, so this is the metal, and this is another pole. Yeah, okay. So we have this amperemeter, and this is this photocell. Okay. So this is the experimental result of photoelectric effect. So as the intensity increase, so the photoelectron is also increased, but the same energy. Okay, the red light or the lowest F, okay, the lowest frequency, cannot cause the release of the electron. Okay, so the electrons are not excited and released from the atom. Yeah. But in this case, the electron is not released, is not excited and released from the atom for red light, because this is F is the lowest frequency. So the light with high frequency like violet also, because we can detect the ampermeter moves, yeah. So we can detect the current. Okay. So this is this high frequency light, such as ultraviolet, violet, or ultraviolet. Okay, and then Einstein in 1905 formulated the theory of photoelectric effect by introducing the quanta. We call it photon. Okay. So he used the Planck formulation of black body radiation, Planck theory of the black body radiation, that the energy of the photon is also proportional to frequency. Okay. If F increase, then E also increase. Then electron have greater probability to excited and release, yeah, from the atom. So intensity, we increase the intensity means that we increase the number of the photon. Okay, and this generalized the Planck result the Planck result for the light, and he get Nobel Prize in around 1905 because of this photoelectric effect. So this Einstein theory, this is the relation. Sorry, this should be H and not capital. This HF is equal to kinetic energy plus phi. Phi we call it I don't know in English. Yeah, work function in English. Consider this work function. So somehow this is the minimal energy of a photon that can be released the electron. So electrons at rest, okay, from orbital, and it released but at rest. That's the minimum. So for example, the work function for silver is 4.73 electron volt. Okay. So we get that this this means that we have this is the minimum, the minimum energy. So it means that HF minimum is equal to 5. Okay. So this phi here is the work function is H times F minimum, with the kinetic energy is 0. Is there any question until this lecture before we continue? Hello, hello. Any question? Any question? So sorry. Okay, this formula, we call it this Einstein relation of photoelectric effect. Somehow the energy of the incoming photons is equal to the kinetic energy of electron and the work function phi. So for example, is for silver, we have the work function is 4.73 electron volt, okay, and determine the minimum frequency for electron released from the silver, from the atomic silver, okay. So the minimum frequency, it means that we have the kinetic energy vanishes or equal to 0. Then using the Planck formula, we get that the minimum frequency of the light, it should be 1.14 times 10 to the 15 hertz. Okay. So the Millikan is somehow is the famous experimentalist at that time. He also proved the relation of Thomson relation between charge and mass of the electron, and somehow he measured the unit charge, the unit charge, or in this case the unit the electron charge, which is equal to 1.60602 times 10 to the minus 19 coulomb. Okay. He also measured that charge, the electron charge, the unit charge in this case. So Millikan also want to measure this relation, okay, this Einstein relation. So we call it this Q V0 is the kinetic energy. Okay. So basically, initially, this Millikan did the experiment to oppose this relation. Okay, but the fact is the fact. Okay, but he had this curve. Okay, this linear curve, which shows that that this relation is correct. Okay. This is the Millikan measurement, and he also obtained the Nobel Prize, yeah, for this experiment and also the experiment for measuring this unit charge. So the last is about this Compton effect. So Compton effect means that we have an X-ray, okay? So X-ray that's bombarded, for example, gold. Yeah, the target is a gold. Somehow this X-ray scattered this electron shell, yeah? This outer electron shell in the atom, and be scattered, yeah, and release, okay, and then also this X-ray, this incoming X-ray, and then this is the scattered X-ray, okay. In classical theory, you know that we do not have this shifting frequency. Okay, for example, if the light, for example, collide, for example, with coming from the air to the glass, okay, to the medium, we do not have any shifting frequency. Okay, a shifting frequency. Okay, but in this case, the frequency is shifting. So this proof that this proof of the photon theory of the Einstein, yeah, that the light can be viewed as the particle. Okay, so the light at the beginning is the electromagnetic waves. Okay, but as the energy increase, we could consider it as the particle. Okay, so this is the conclusion about this light dualism properties. So the wave can be reflected, refracted, interference, and diffraction. Okay, but not the photoelectric effect. Particle can be reflected and refracted, but it cannot show interference pattern or diffraction patterns. Okay, but electric effect, yes. So this is at the end of our lecture today. Is there any question? Any question? No question. Hello? No question?
No, sir.
No, sir.
Okay. Let's make attendance here. The attendance. Just a moment. This week is the last week, yeah, of the lecture, yeah. Okay. Okay, you can log in to 6, okay, and then checklist your attendance today, yeah. Okay.